All right, chapter 10 and 11, explanation video. Chapter 10, independent measures t-test. All right, that consists of using two separate groups, comparing them against each other, and seeing if there is a significant difference between the two groups. So, two rival college fraternities brand themselves on riding off-road vehicles. Fraternity A's vehicle of choice is the ATV. Fraternity B's vehicle of choice is the dirt bike. Each fraternity claims that their off-road vehicle of choice is faster in a mountainous terrain setting. They took their best 15 riders each and faced off. The goal was to have the fastest average top speed on a mountain trail. All 15 riders from each group's top speed were measured. Fraternity A's 15 riders finished with a higher average top speed. Question: is the ATV significantly faster in the mountains than the dirt bike? Use an alpha level of 0.01 to answer. All right, so what information are we given? Well, we're given the N, which is the number of participants in each group in this case. So fraternity A, there's 15 participants. Fraternity B, there's 15 participants. The mean speed of each group. So fraternity A is 40.8 and fraternity B is 34. And the sum of squares, which we all know how to calculate, so you'll be given to it now moving forward when it comes to independent measures t-test. It is 510, and the sum of squares for fraternity B is 414. All right, so like with all t-tests, you'll have to know how to state the null hypothesis and the research hypothesis. First thing you always want to think of before you write your hypothesis, how many tails is the test? Well, in this case, if you look at this sentence right here, is the ATV significantly faster in the mountains? So that keyword faster in the mountains is claiming we're looking for a direction. So when it's a directional hypothesis, that means it's a one-tailed hypothesis. So I'll do the research first. Students seem to think it's easier. So ATVs are significantly faster in the mountains than dirt bikes. That would be the research hypothesis, right? That's what we're hoping to find to be the case. And then the null hypothesis in a directional hypothesis is you're stating the opposite or the same as the research hypothesis. So in this case, ATVs are significantly slower in the mountains or the same as dirt bikes. Okay. Is this a one-tailed test or a two-tailed test? It's a one-tailed test. Okay, so independent variable. The independent variable is also known as the manipulated variable, right? And there's at least two levels. And in this case, the off-road vehicle is the independent variable, and the two different levels are the two different types of off-road vehicles being measured against one another, which are ATVs and dirt bikes. And a dependent variable is also known as the measured variable. In this case, it's speed. All right, so now degrees of freedom. So, unlike a single sample t-test where you only get 1 degrees of freedom, since we're using two independent groups of a sample, we're going to combine the 2 degrees of freedom, which is also labeled as DF total, of both groups. So in this case, the groups just happen to be equal size. So you are going to do, you could do one of two ways. You could do 14 minus 1 plus 14 minus 1, which is 28, or you could do 15 plus 15 minus 2, which is 28. So now we have the critical t value, and we have to go look for it. So we get the critical t value. Okay, there it goes. We get the critical t value the same way we did it for a single sample t-test in the previous chapter. You got the degrees of freedom. You got the tails of the test, and you got the alpha level. So in this case, you're going to look at an alpha level of 0.01 at a one-tailed test with a degrees of freedom of 28. And when you look that up on the table, you will see it says 2.467. Now, it's always very important on a one-tailed test to indicate the correct sign of the critical t. So in this case, we're looking for significantly faster. So in that case, we're going to be using a positive. So that's why the answer is plus 2.467. All right, so the population mean difference is always 0. Go back to the lecture if you want to know why, or read the textbook. Sample mean. Well, these are given, so the sample mean's given. The sample mean of the group 2 is given. Sum of squares is given. And the sum of squares of group 2 is given. All right, so this stuff was given to you. Again, we've been tested on this. I know everyone by now knows how to compute a mean and compute a sum of squares. So you're given this information, and we're going to move forward. So now we are going to do a sample variance of each group. So the sample variance of group 1 is the sum of squares of group 1 divided by the degrees of freedom of group 1. And the sample variance 2 is the sum of squares of group 2 divided by the degrees of freedom of group 2. You should come out with these answers. And now we have to pool the sample variance. Basically, we're combining the sample variance. So you just follow this formula. So you can see here where I wrote out the work. Best way to do it is do the degrees of freedom times the variance of the first group plus the degrees of freedom times the variance of the second group. So it's df1 times variance 1 and df2 times variance 2. And then that's divided by degrees of freedom 1 plus degrees of freedom 2. So that comes out to be 510.02 plus 413.98 equals 924. So 924 divided by 28 is 33. 33 is the pooled variance. All right, and now we need to get the standard error of the mean difference. This will be the denominator of the t-test. So what you do here is you take the square root of the pooled variance divided by n1 plus the pooled variance divided by n2. So in this case, the n's are the same for each group, which is not always the case, but in this case it is. So you just do 33 divided by 15 plus 33 divided by 15 equals 2.2 plus 2.2 equals 4.4. And then the square root of 4.4 is 2.1 rounded. All right, so now our t obtained. We are going to just look at this first part, all right? The population mean difference, as I said before, is always equal 0, all right? Because underneath the null hypothesis, we are stating that there is no difference between the population means. So the population mean difference is 0. So anything minus 0 is what? Well, whatever it is. So moving forward, if you look forward and look at test 2 formula sheet, the formula for an independent samples t-test does not have this second part. There's no need for it because it's just a waste of time as far as computing goes. So you just take the mean 1 minus mean 2 over the standard error of the mean difference, which we just computed, and that comes out to 3.238. Now we compare 3.238 to our t critical of positive 2.467. And our t obtained is larger than our t critical, so we reject the null hypothesis, and we have significant results. We could say that the ATV is faster than the dirt bike, and we could say the ATV is significantly faster than the dirt bike in a mountainous terrain setting. All right, and then for an independent measures t-test, on most research articles, you'll see Cohen's d reported with that. So that's why I'm having you guys compute Cohen's d when it comes to an independent samples t-test. And you just take the mean 1 minus mean 2 over the square root of the pooled variance. Now, Cohen's d, this number represents the difference in standard deviation. Could be a test question. So Cohen's d measures the distance in standard deviation of the two sample means. All right, so 1.18, that's a very large distance. All right, so there is a very large effect as well as a significant result in this study. All right, chapter 10, second question. I'll go through this one a little faster since I just was pretty thorough in that first one. So chapter 10, you got 20 students randomly assigned to an experimental group receive an instructional program. 30 in a control group do not. After 6 months, both groups are tested on their knowledge with a knowledge test. The experimental group has a mean of 38 with an estimated population standard deviation of 3. The control group has a mean of 35 with an estimate population standard deviation of 5. Is there a difference between the two groups' knowledge? Using the 0.05 level, what should the experimenter conclude? Well, what's the null hypothesis? Well, what are we looking for? We're looking for just the difference, right? Is there a difference? Right? That's the key word, letting you know how many tails will be in this test and also how to write the null in the research hypothesis. So there is no difference between the knowledge of the control group and experimental group, and the research on a two-tail test is just the opposite of the null. There is a difference between the knowledge of the control group and the experimental group. All right. One-tail test, two-tail test. Two-tailed, the keyword is difference. Independent variable is the instructional program, and the two levels are you're either given the instructional program or you're given no instructional program, and the dependent variable is the measured variable, and what is being measured is knowledge. Degrees of freedom, unlike the first question, there are not even equal-sized groups, right? There was 20 students in the first group, 30 students in the second group. All right, but it's the same thing. You can either add those two, and you can either add the two ends and minus 2, or you could just do 20 minus 1 and 30 minus 1 and add them together. Either method you choose, you'll get 48 for DF total. Now, you go to the chart the same way. Two-tail test, alpha level of 0.05 this time. Always, be careful on what alpha level they're asking for. And you're going to go. So when you go there, you're going to see that it goes from 40 to 60. So in the case of that, you are always going to use the lower number. Why? Because it has the more extreme T critical value, a larger T critical value, and we never want to overestimate what we're trying to measure, right? So we rather say if it's significant, we rather say it's significant at a higher T value than a lower T value, because we could be sure that it would be significant. All right, so you always use the one above it. As far as your test goes, you will be given a degrees of freedom that is directly on the table. All right, population mean difference, always 0. Sample means given. Sum of squares not needed, right? We don't need the sum of squares because why? We're given the estimated population standard deviation of each group. So now what are we looking for here? Sample variance 1 and sample variance 2. Well, what are we given? Well, we're given the estimated population standard deviation. Well, the variance is always the standard deviation squared, right? So the standard deviation squared equals the variance, and the square root of a variance equals the standard deviation. So in order to get the sample variance 1 and sample variance 2, all we are going to do is square those standard deviations that were in the question. All right, we'll get it. 3 squared is 9, 5 squared is 25. Plug them into this formula, you'll get 18.67. And then plug the pooled variance into this formula for the standard error mean, you'll get 1.24. T obtained, you'll get 2.419. 2.419 is larger than the critical T value that we are comparing it to. Decision on the null, we are rejecting the null. Again, we're going to do a Cohen's D. Mean 1 minus mean 2 over the square root of the pooled variance equals 0.69, and you're done. All right, chapter 11. Now, this is a repeated measures t-test. It's using one group and testing it at 2 different points of time, where in the middle of those 2 points of time, you're given some sort of manipulation to see if there was a difference before and after. So 5 people who were convicted of speeding were ordered by the court to attend a workshop. A special device put into their cars kept records of their speeds for 2 weeks before and after the workshop. The maximum speeds for each person during the 2 weeks before and 2 weeks after the workshop are as follows. Using the 0.05 significance level and 5-step of hypothesis testing, which is what we're doing, should we conclude that people are likely to drive more slowly after such a workshop? So you're given the sample data, 5 participants, their before speeds and their after speeds. Okay? And the independent variable would be the workshop is different levels here. Again, you won't be asked this on your test when you attend the workshop right after and you did not attend a workshop before. And what are we measuring? The speed. The research hypothesis will be those who attended the workshop drove slower after the workshop than before. Right, we're writing the research hypothesis first here. So in this case, right, what are we looking to see? We're looking to see if after you're given this workshop, you drive slower. So the no would be those who attended the workshop drove faster or the same than before the workshop. All right, so now you have to get the mean of the difference, right? That's symbolized as MD, okay? And that's the sum of the difference divided by N. So how do we do this? Well, we're given this in the beginning. So you just make this table. You'll see it on your sheet empty. And before scores and after scores, you do after minus before, right? You never do before minus after. Because to see the difference, you want to subtract what happened before from after. So it's after minus before. You add these up, you'll get a negative 20. Negative 20 divided by N, which is 5, is negative 4. So the mean of the difference is negative 4. All right, so now we could compute the sum of squares, right? This looks just like the definitional formula sum of squares chart table that we did in chapter 4. So what do? We do each x value minus the mean difference. So the x value in this case will be this after minus before score. So you take this after minus before score and subtract it from the mean, which is labeled as MD, which is mean difference. And very similar, right? We're taking deviations from the mean. Then we're taking the sum of the deviations from the mean squared. We get the sum of squares of the mean difference. All right. How do we get the sum of squares? Use the table above. Again, you just add up that last column. All right. So now how do we get the estimated variance? Same way we always do. We take the sum of squares divided by n minus 1. And this is the standard error of the mean difference, okay? So how do we get that? We get the square root of the variance divided by n. Compute that. It will come out to 1.14. T critical. All right, so the degrees of freedom here, it's not 2 groups like independent samples t-test. It's the same group tested twice. So you're only going to measure that degrees of freedom once. You're not combining them like you did in the previous chapter. So there's 5 participants. 5 minus 1 is 4. We're looking to see if they drove slower. So it's a 1 tail. Alpha level of 0.05. Now, be careful here. So everyone should go to the table and you will get 2.132. But in this case, it's going to be a negative 2.132 because we are looking to see a significant change in the slower direction, which is in the left side of the distribution, which is why this critical value is a negative. T obtained. Again, the difference, this mean difference right here, the population mean difference, hypothetically under the null hypothesis, is always 0. All right, so again, looking ahead to the test 2 formula sheet, the formula is just MD over SMD, right? Because you're just subtracting 0 because the population mean difference is 0 under the null hypothesis. So you do negative 4 divided by 1.14 equals negative 3.509. And then we're doing an R squared where we're taking the T obtained squared divided by the T obtained squared plus the DF. All right, and R squared, what is this? What does R squared mean? This could be on your test. R squared means the percentage of variance explained by the manipulation of the independent variable. Your book defines it as the percentage of variance explained by the treatment effect. They mean the same thing. All right, so obviously the closer this is to 1, the stronger the test was, right? If 75% of the variance can be explained by the manipulation of the independent variable, it's basically saying 75% of the difference between the two groups in this test can be explained by the workshop. Decision on the null, we're going to reject the null, obviously, because RT obtained is larger than RT critical. Okay, chapter 11, second question. 5 sophomores were given an English achievement test before and after receiving instruction in basic grammar. The mean difference score is negative 0.4, and the estimated variance for the difference score is 8.3. Using the 0.05 significance level, is it reasonable to conclude that future students will show higher scores than instructions? So as you're reading this, higher, we know it's a one-tailed test, all right, and it's 0.05 level. We could skip the independent, dependent variables. Again, I'm sure you all understand that. And how it looks on your test is going to start with the research hypothesis or the null, either one. So what's the research hypothesis in this case? Those given special instructions after the English achievements test will score higher than they did before given special instructions. Those given special instructions after the English achievement test will score lower or the same than they did before given special instructions. Again, it's a directional hypothesis, so the null must state the opposite or the same. The mean of the difference, given, negative 0.4. The estimated variance is given, 8.3. Estimated standard deviation of the mean difference, we just take that variance, divide by n, and get the square root of it, 1.29. T critical, you go to degrees of freedom, one-tailed, 0.05 on the table, come out to 2.132. You know it's going to be a positive 1.32. And RT obtained, we're just taking negative 0.4 divided by 1.29 is negative 0.310. Our R squared is the T squared. The T obtained divided by the T obtained plus DF comes out to 0.023. And so that's a very small R squared number. That's a very small T obtained number. So we are going to fail to reject the null here. Right, RT critical was 2.132, and this is 0.310. So this is not there's no significance going on. We are going to fail to reject the null hypothesis in this case. All right, so we're done with t-test. Next chapter, we will be doing ANOVAs.